Hello, I'm Seema and welcome to part 18 and the last part of the chapter Periodic Classification of Elements. In this video, I'm going to tell you about some anomalous properties of the second period elements, and we'll also discuss the periodic trends and chemical reactivity and conclude this chapter. Let us start with anomalous properties of the second period elements. We notice that the elements in the second period, they usually display properties which are a little different from those elements that lie below them in the same group. We have seen that the properties of elements are as a result of the electronic configuration, and since elements in the same group have the same outer electronic configuration, they display similar properties. But the second period, that is the second period which have only two shells in them, they usually display properties which are a little different. What are the reasons for these different properties, and what are these properties that we see? One thing, lithium and beryllium, unlike the alkali and the alkaline earth metals, they tend to form covalent bonds instead of forming ionic bonds. We expect alkali and alkaline earth metals to form ionic bonds because they have 1 and 2 electrons in their outermost shell, which they can lose very easily because of the extremely low ionization enthalpies that they have. You have to use very little energy to remove the electrons. But in the case of lithium and beryllium, they are very, very small in size, and the amount of energy required to remove the electron from so close to the nucleus is rather high. So they, instead of forming ionic bonds, they prefer to share electrons. Instead of losing electrons, they prefer to share, and hence they form covalent bonds, while the rest of the members in the group, they predominantly form ionic bonds. Another very remarked thing that we observe is that these elements, which are in the second period, instead of being similar to the elements which are below them in the same group, they tend to have a greater similarity for the element which falls below it in the next group. That is, which falls diagonally below it in the next group. So, lithium is more similar to magnesium. Beryllium is more similar to aluminum instead of being similar to sodium. One property I have written here is the atomic radii, the metallic radius of these elements. Lithium has a radius of 152, sodium has a radius of 186, and magnesium, if you see, has a radius of 160. So 152 is closer to 160 than it is to 186. You can see the same thing here. Beryllium has a radius of 111 and the radius of magnesium is 160, while the radius of aluminum is 143. And we find that the metallic radius of aluminum is closer to beryllium than beryllium is to magnesium. So this kind of a diagonal similarity is known as diagonal relationship. What are the reasons for these anomalous properties? Why are the second period elements different? I've listed a few reasons for this. The first reason is that the second period elements have exceptionally small sizes. The reason is simple, they have only two shells. And the first two shells, the nucleus, is very, very small. And the two shells around it obviously have to be extremely small too. So these two shells around the nucleus, they are very small and very close to the nucleus. But for the third period, that is sodium magnesium, there are three shells, and the third shell is larger. So one reason for the exceptional properties is that they have extremely small size, and that's the reason why they predominantly form covalent bonds instead of forming ionic bonds, which logically they should have formed by losing 1 or 2 electrons. The next thing is that they have a large charge over radius ratio. Again, this is actually the same thing. The radius is so small that the charge over radius ratio makes it a very large ratio. It becomes important, it becomes very significant. But in the case of the third period elements, the radius is larger and the charge that is increased is actually the same. This has one positive charge, this will also have one positive charge, but the radius is much larger, therefore charge over radius ratio becomes smaller. Since the charge over radius ratio becomes smaller, since the denominator is larger here in the third period, the charge over radius ratio is not so large, and therefore this affects the properties of the second period elements, that their charge over radius ratio is very large. The next thing is that they have high electronegativities. What is electronegativity? Electronegativity is the property by virtue of which atoms tend to pull a shared pair of electrons towards themselves. If the size is smaller, naturally the electrons are closer to the nucleus and hence the effective nuclear charge would be more. They would experience greater attraction by the nucleus and therefore they would have higher electronegativities in comparison to the other members of the same group. And that also renders different properties to them. Then the next fourth reason is that the second period has only 4 valence orbitals. That is, the second period has 2s and 2p orbitals. 2s is only 1 orbital and 2p orbitals are 3 orbitals. So they have only 4 orbitals. And if they have only 4 orbitals, they can have a maximum capacity of 8, and whatever they run short of in that 8, they can combine only, they can show oxidation states or a combining capacity only which extends to that number 8. So their combining capacity is limited. But in the third period, if you see, the third period has 3s, 3p and 5 3d orbitals too. So 5, 6, 7, 8, 9. They have 9 orbitals. And if they have 9 orbitals, they can expand their valencies, they can expand their oxidation states beyond the 8 too. They can go up to 18 electrons. So they would show they have a greater versatility or a greater diversity in the compounds that they can form, while the elements which belong to the second period have limited options. For example, boron forms Bf4 ion, where it shows a capacity of only 4 electrons, that is 4 pairs of electrons. But aluminum, it forms Alf6 3 negative. So it is combining with 6 fluorine atoms. So combining the number of electrons that it can accommodate is definitely greater due to the availability of the 3d orbitals. The fifth reason for this is that they have greater p-pi bonds. Since we've not done chemical bonding as yet, let me just tell you about the pi bonds. When an atom forms bonds, the 2p, that is the second period elements, are very small in size. The bonding, covalent bonding, is formed when orbitals overlap each other. And when they overlap, the overlapped area is where the electrons that are shared are usually present. That is how we perceive it. That the electrons, although we know the quantum mechanical model of atom tells us the electrons can be present anywhere, but yet the chances of finding the shared pair of electrons would be greater in the area of overlap. So we also know the shapes of p orbitals. The p orbitals are shapes of dumbbells. So if they combine, they overlap, the two dumbbells of two atoms, let us say this is the nucleus and this is the one lobe of the dumbbell, they overlap to form the first bond. And the head-on overlap is known as a sigma bond. Alright, that is the first bond. The second bond that is formed would be now, if this is along the x-axis, the next p orbitals would be along the y-axis. So this next bond would be formed when the two lobes of the p orbitals along the y-axis, they overlap each other. On the top lobe and the bottom lobe, they overlap. And then the second bond is formed. Such a bond which is formed by the sideways overlapping of p orbitals is known as a pi bond, and it is the second bond between the two atoms. So if a third bond has to be formed, then you can say this is x-axis, this is y-axis, and let us imagine that this is the z-axis. Then these two z orbitals should also overlap sideways and then form the third bond. So this is what happens when the p pi, the p pi, that is pi overlap. So p pi bonds, that is multiple bonds, are possible only in the case of the second period elements. The reason for it is so simple that they are so small in size that there is a possibility of the p orbitals coming so close that they actually overlap. So carbon combines with carbon itself to form a double bond, that is one single. The first bond is the sigma bond, so the second bond is a p pi bond. C triple bond C, the first bond is a sigma bond, but the other two bonds would be formed by the other two p orbitals along the y and the z axis. Similarly, nitrogen can form double bonds, triple bonds. Carbon and oxygen can combine with each other to form double bonds. Carbon and nitrogen can form a double bond, they can form a triple bond, and nitrogen and oxygen can form double bonds. So we find that these p pi bonds are possible only in the case of the second period elements. Why? Because their size is so small that a sideways overlap is possible. But for a 3d orbital or a 3p orbital, the third shell is larger. The sigma bond may be possible, but for the pi bond, the two lobes are far further away from each other, and a sideways overlap at that distance is not possible. So this is also one reason why they show anomalous properties. The elements of the second period, they can form p pi, that is multiple bonding with themselves or with other atoms of the same period. But elements of the third period are unable to form these multiple bonds with themselves. So these were the properties due to which the second period elements show some anomalous properties, and they also display diagonal relationship. We now come to the last part, just a little synopsis of the chemical properties and the periodic trends in chemical reactivity before I wrap up the chapter. We have studied that the properties of elements are actually due to the electronic configuration. You can use the electronic configuration of an atom to explain everything, right from the size of the atom, the physical properties, and the chemical properties. All of them can be explained on the basis of the electronic configuration. So we notice in the periodic table that as we moved from left to right, the metallic character, it decreased. And as we move from right to left, the metallic character increases. So from left to right, metallic character decreases, so non-metallic character increases. And from right to left, or on the left side, we find to be, just to put it in another way, on the left side we see all metals, and on the right extreme, that is, we are excluding the noble gases, the halogens and the chalcogens, we find them to be non-metals. So on metals to non-metals, and in between we would have metalloids. So we find that in the entire periodic table we see a gradation of these properties. The electron gain, the size of an atom, it decreases as we go across a period, and it increases as we go down the group. Similarly, the electron gain enthalpy, that is the energy which is given out when it gains electron, that is the negative nature of it, increases as we move from left to right. And it decreases as the electron gain enthalpy decreases as we move from top to bottom. The electronegativity, that is the tendency to pull a shared pair of electrons towards itself. The non-metals are electron deficient. They need electrons, so they have a stronger tendency to pull the electrons towards themselves. So electronegativity increases as we move towards nonmetals, that is towards the right of the periodic table, and electronegativity, due to the size, as you move down in a group, the size of an atom increases, and hence the further away the electrons are from the nucleus, the lesser will be their tendency to pull the shared pair of electrons towards themselves, and therefore electronegativity decreases as you go down the period. So these are the trends in physical property that we observe only because of just by the knowledge of the electronic configuration of these elements. We also notice one thing, that metallic oxides, that is, if metallic oxides are formed, they are basic in nature, and non-metallic oxides on the other hand are acidic in nature. So we say metallic oxides are basic oxides, non-metallic oxides are acidic oxides. If you dissolve a metallic oxide in water, you will get a base. But if you dissolve an acidic oxide in water, you will get non-metallic oxide in water, you will get an acid. And in the middle then, just like we had metals, non-metals and metalloids, the elements which are closer to the middle, they would form amphoteric oxides. Amphoteric oxides are neither acidic nor basic, right? So, or we could say when they act with acids, when they react with acids, they act as bases, but when they react with bases, they act as acids. So they are actually somewhere between acidic and basic oxides. So these are the different trends that we see in the chemical reactivity. Okay, how about the reactivity? This is the last point. We find that these on the extreme left are strong metals. They have a strong tendency to lose electrons. They lose electrons very easily. If they lose electrons very easily, it means they are very reactive. But I also told you that losing or gaining one electron is easy, 2 difficult, 3 very, very difficult, and 4 is almost impossible. So as we move from left to right, in order to acquire stability, atoms have to lose 1 electron, 2 electrons, 3 electrons, 4 electrons. So how would you expect the reactivity to change? You'll expect the first group to be very reactive, second group less reactive, third lesser, fourth group, that is the 14th group, we are talking of representative elements, would be even lesser reactive. But 15th group now needs 3 electrons. So it can either share 3 electrons or it can gain 3 electrons. But gaining 3 electrons, difficult. So reactivity comes down at 4, but then from 4 to 3 to 2 to 1 in halogens, it goes on increasing. Now the halogens need to gain only 1 electron, so they are the most reactive. So what do we see what is the periodic trend in reactivity? We find that as we move from left to right, the reactivity of the elements first decreases and then it increases, right? The transition metals and the inner transition metals, that is the lanthanide and the actinoid series. In these, the last electron which is adding is not going to the outermost shell. It is going to the penultimate shell in transition elements, and it is going to the inner penultimate shell in lanthanide series. So as we move from left to right, we say the size of an atom decreases, but that decrease in size is less pronounced in the case of transition metals and even lesser pronounced in the case of lanthanide series. So that is because the electron is not adding to the outermost shell, it is adding to the inner or the inner penultimate shell. The penultimate or the inner penultimate shell. Therefore, their trends are a little different, which you'll study when we study these chapters. So we'll study more of the chemical periodic trends, and we might revise a little bit of these physical periodic trends as and when we do these chapters. So with that, we come to the end of this chapter. Thank you for watching. If the video helped you, please give it a like, subscribe to my channel, recommend it to your friends, and keep returning for more videos in chemistry. Thank you and bye-bye.